My name is Alexandra Sipershteyn, and I want to thank you so much for coming to my presentation. I only had to bribe a few of you and not the regulators. So all of you, I really appreciate being here. So all of you guys have your mercury under control, but every once in a while you see a higher than expected mercury number. And as per usual, the SEMs are blamed. Well, this presentation is going to focus around what else might be going on and where you should start to look when mercury starts to rise unexpectedly. Ohio Lumex is a family-owned company located in Solon, Ohio. We're manufacturers of mercury analyzers and other monitoring tools for the power industry. We have more than 20 years of experience around mercury measurements specifically. We have experts on our team with really diverse experience, and we're continuously doing research and development to innovate for the industry to provide simpler and more cost-effective solutions. In the lead up to MATS, many plants were able to achieve mercury reduction as a co-benefit of existing control devices. Other plants installed control technologies to exclusively focus on mercury control, like activated carbon injection or FGD Re-Emissions chemicals. Some plants started injecting calcium bromide onto the coal for increased mercury oxidation, and others turned to refined coal. But with economics and aging equipment, strategies are continuously changing. And as you guys change your strategies, we're often involved in the evaluation process of assessing what is not working or optimizing those new strategies. We've been involved in some very interesting testing and have noticed some common patterns when concentrations of mercury increase unexpectedly. So what are some of these patterns? Could your equipment be contaminated and contributing to high mercury levels? Is some of your control technology equipment not working optimally or properly? Is the ammonia slip higher than expected and inhibiting mercury oxidation? Is mercury concentration increasing due to arsenic poisoning of SCR catalyst? How is SO3 contributing to problems with mercury control? Is that FGD Re-Emissions and how you can tell? What is FGD Slurry Partitioning, and can evaluating it help you with mercury control? And why do we see high mercury upon startup after a planned or unplanned outage? Now that is a lot to cover, and I'm probably not going to be able to do the most thorough job. I might only be able to cover the most important bits, like borat. But if you want to discuss in greater detail, feel free to find me later, contact me, email me, and we're also turning this into a series of blog articles with much more detail, so I can send those your way as well. So, could your monitoring equipment be contaminated and contributing to high mercury levels? The traps. The sorbent traps are not packed airtight, and there is a possibility for mercury permeation from the environment. We have seen this before, where a customer reported high mercury levels on virgin sorbent traps and then realized that they were storing the traps in a vehicle which previously had a mercury spill in it. Another customer reported contamination from shoes after a mercury spill in a lab tech's home. Please store your sorbent traps in a location where you are certain that mercury ambient levels are minimal. Oh, and don't store the traps near sampling equipment that may be contaminated either. So what can you do about it? You can audit your environment with an ambient air analyzer. You can also utilize your M324 spectrometer in ambient air analysis mode. Contact me for details. But really, the actual spectrometer portion of your M324, that rectangular, longer blue box, can literally be disconnected from the furnace assembly. A hose can be attached onto it, and you can literally sniff the environment to figure out if there's any potential mercury contamination. We use that same exact spectrometer anytime that we go to ambient air shows, and I literally demo that spectrometer by having customers exhale near the tube, and it can quite literally tell you how much mercury you're even exhaling via your dental amalgam fillings, silver fillings that might be in your teeth. You can also set up a sorbent trap sampling system and sample some sorbent traps in the location temporarily, or you can even just lay out some carbon in a dish in the environment for a period of time and then analyze it to see if the ambient air where you're storing the traps is contaminated. That sorbent is just going to absorb everything that it possibly has the ability to. That's what it's really good at. You will also want to analyze virgin sorbent traps every once in a while to confirm that nothing has changed. Is your equipment contaminated? Let's talk about the shroud. Many are sampling post-wet FGDs. It's important to keep traps dry, so you guys are utilizing probe shields or shrouds, which allow for traps to sit recessed a few inches with a metal umbrella protecting them from direct moisture entrainment. But that shroud could become a source of mercury. In a saturated environment, the moisture will release mercury from particulate or sludge buildup on the shroud in the form of vapor phase oxidized or elemental mercury. Some of the oxidized mercury released from this source may be captured on the front plug. However, much of it will be captured on the first carbon section over a typical 7-day run. Suddenly, a source that usually has a mercury concentration much lower, like 1 microgram per dry standard cubic meter, has a much higher mercury concentration than expected. And over time, it seems to get worse and worse. Often, it's minimally affected by additional activated carbon or calcium bromide injection. So what can you do about it? In this case, the best advice we can give you is to clean your shroud. We sonicate ours. Or even better, have a second shroud readily available to swap with each trap changeout. The probe. In the same way as the shroud, the probe itself can become a source. This is especially important for stack testers who are taking their equipment from plant to plant. Think about where the probe was last used. High mercury gold roaster, then to a Lee source may be a problem. So what do you do about it? You check your probe, your storage cases, your vehicles, and other equipment for contamination, and then you take it through a decontamination procedure if necessary. I have a thorough SOP on this, so if you want it, just email me. I'll be happy to send it your way. So how do we do it? First, we need to detect. Just like checking the environment, an ambient air analyzer can be used to sniff inside cases, boxes, and equipment to detect elemental mercury off-gassing. But there most likely will be mercury in oxidized form attached to the surfaces, like particulate, which cannot be detected with an ambient air analyzer. However, it can be detected using something that we call the swab method. Using clean utensils, take a small piece of glass wool, drop a couple of drops of clean water onto it, and swab it across the potentially contaminated surfaces. We typically swab 3 times across the longest surfaces of cases or even the length of a probe. The glass wool swab then gets analyzed in an M324 system. If you don't own an M324 system, why don't you own an M324 system? No, I'm just kidding. If you don't own one, we analyze material all the time. So you can always send it to us. We'll be happy to do it for you. And for us, any sample over 10 nanograms is considered contaminated. But 10 nanograms might be overkill for some locations. So you need to use your discretion on if a higher wipe sample mass is acceptable for the location where you are doing testing. If this equipment is to be used at a low-level source in the future, then 10 nanograms on a wipe sample is appropriate. Then we decontaminate. Sulfurated potash dissolved in water can be used for this. I don't have the exact proportions, but we put a nickel-sized amount of sulfurated potash in a large spray bottle filled with water, shake it up, and then generously spray the solution all over the equipment. Let the solution sit and react on the surfaces for about an hour, and then we wash off the solution. If possible, we even use a pressure washer. Heavily contaminated equipment will need more treatments. Repeat the swab test until fully decontaminated. We treat the equipment until the swab test shows under 10 nanograms. because handling equipment with any more contamination can ruin pair agreement and bias your results high, especially when you're working at a low-level source. If you suspect that you have higher mercury because some of your control equipment is not working, you have to find a starting point. Is the SCR not oxidizing mercury as well as it should? Should you increase the halogen injection, or is it the FGD and potential re-emissions? Speciation sorbent traps are an excellent tool to help you evaluate where you should look, but be wary. Mercury speciation sorbent traps are very temperamental. They are extremely temperature sensitive. Around the SCR, you absolutely must use a cooling probe, but you don't want to cool it too much. If the traps are sampled at temperatures that are too high, you will have biased low oxidation, as the oxidized mercury will break through to the elemental mercury sections, thus underestimating your oxidation rate. At temperatures that are too low, you will get condensation in the traps and a scrubbing effect that leads to overestimating your mercury oxidation. Temperature is tough to control. You must have temperature measurements in the exact location where the trap sections actually sit, which is further complicated because we have varying length of traps. We make traps that range from 185 millimeters long to 450 millimeters long, depending on the source conditions. And we even sometimes will vary the section lengths. Unfortunately, a stationary thermocouple is just not exact enough for speciation sorbent traps. This is why we utilize cooling and heating in our probes, as well as a fine temperature controller, which incorporates an inline thermocouple. This thermocouple controls the probe temperature from the exhaust of each trap, literally inserted into the back of each trap. Flow rate is another variable that is important to get right. Equipment with dry gas meters is limited by the low end in terms of flow rate, but sample at too high a flow rate and you break the physical bonds that are formed by the oxidized mercury sorbent, causing breakthrough and underestimating your oxidized mercury ratio. Analysis must be done on site, as sampling parameters will most certainly need to be altered during the testing based on your results. Sampling duration is also something to think through. Oh, and particulate, another thing that will need to be controlled. Particulate entrainment often contains halogens that can scrub elemental mercury and bias your oxidation rate high. There's a fine balance that needs to be struck between all of these variables. So let's talk about ammonia inhibiting mercury oxidation. As SCRs are being forced to operate at lower temperatures, ammonia bisulfate is more likely to condense on catalyst surfaces, causing fouling, pluggage, and issues with denox. Overinjection of ammonia becomes more and more necessary. Ammonia slip measurements have traditionally been used as they relate to SCR performance for NOx reduction and to minimize overinjection for economic reasons, as well as to minimize air heater pluggage. But ammonia concentration is also strongly related to mercury oxidation. In the presence of ammonia, competitive adsorption between ammonia and elemental mercury on SCR catalyst is partly responsible for weakening mercury oxidation. Ammonia consumes surface oxygen on the catalyst, which also results in lower mercury oxidation rates, especially in the absence of gas phase oxygen. More importantly, oxidized mercury can be reduced by ammonia to form elemental mercury with the aid of nitric oxide. If you are seeing higher than expected mercury, evaluating your ammonia slip is imperative. It is quite possible that your ammonia is dramatically affecting your mercury oxidation potential. Actual field measurements are the best way to evaluate this. So when Dad and I used to test on site together, this was us about 10 years ago, Dad would say every once in a while, I think we might have a substantial ammonia slip issue. And I remember the very first time that he told me about this, my reaction was, "What? I only peed a little when I sneezed." This was shortly after I had a baby. Unfortunately, it has become historically difficult to obtain reliable in situ data. The available methods and instruments are expensive and cumbersome when it comes to ammonia measurements. But we're trying to change that by creating tools to easily do these measurements. Ammonia sorbent traps can be used to measure your ammonia slip at various operating parameters. We use them to determine SCR deficiencies, prevent overinjection, and track deactivation over time, which can help to predict catalyst failure. We have even used ammonia sorbent traps to perform interlayer testing to determine rate of degradation for each layer. Here is some data from a test we did in an SCR where we pulled 4 pairs of traps, one between each catalyst layer. You can see a pretty dramatic drop in ammonia as the gas passes through each layer of the SCR until finally we end up with about 2.8 ppm of ammonia leaving the SCR. This is the sort of SCR profile that can be incorporated into a modeling and management plan to get a better sense of what's going on with each individual layer. The slip in this case was within the expected range of 2 to 3 ppm. But one thing we've noticed in the testing that we've done so far is that the ammonia slip is rarely what the plant expects. The theoretical value provided by models or catalyst manufacturers is often off by a significant amount. Incorporating actual field measurements into the models can greatly improve the reliability of those models. The traps are capable of measuring very low concentrations of ammonia with a high degree of accuracy. Normal sample runs are approximately 20 minutes long, but with an extended duration such as 2 hours, it is possible to reach very low concentrations. Our current MDL is 0.06 ppm VD of ammonia in flue gas. Simultaneously sampling mercury speciations traps is also helpful in this evaluation. Typically, it is the 4th or last layer of catalyst where the majority of mercury oxidation reaction takes place. Arsenic. So this actually happened when I was researching arsenic. I was researching SCR poisons. I swear I had to tell my husband as all of the ads came up for arsenic and cyanide when he looked at my computer. So arsenic and how it affects mercury control. I swear, mercury control is what we're really interested in. Arsenic is a known element in fly ash that contributes to SCR poisoning by deactivating the catalyst. The poison may act by simply blocking active sites or altering the adsorption behaviors of reactants and products. This hinders mercury oxidation itself by decreasing the surface area available for the mercury oxidation reaction to take place. It also leads to decreased NOx conversion, which has to be counteracted with excess ammonia. And as we discussed, the requirement to use more and more ammonia leads to a greater ammonia slip and further problems with mercury oxidation. It is not common to use gas phase arsenic measurements for modeling purposes, but it can be an interesting data point if you're seeing unexpected catalyst poisoning rates. Limestone addition has been used to mitigate arsenic poisoning, and optimizing the injection rate is something that is really worthwhile to do. But there has just not been a very easy way to measure arsenic. Method 29 can be unreliable as it was designed for stack measurements, and arsenic has a tendency to condense on the filter, so results are biased low or even 0 in our experience. To support this type of testing, we created arsenic sorbent traps that have been used for several engineering studies to find the ideal injection rate of limestone or lime-based product to mitigate arsenic poisoning. In this project, the client was able to cut their limestone injection rate in half while still seeing the same arsenic mitigation. Although arsenic is referred to as a metal, it is better to consider it as a metalloid. Upon combustion, it forms gas phase oxide compounds which condense into small particles as flue gas cools and may partially exist as aerosols or particulate bound, even at 350 degrees C upstream of the SCR. For this reason, we sample arsenic sorbent traps with an isokinetic sorbent trap sampling system. SO3 and its contribution to mercury control. During the combustion of sulfur-containing fossil fuels, a percentage of the SO2 formed is oxidized to SO3. Further oxidation of SO2 to SO3 across the SCR catalysts can even more than double the flue gas SO3 and sulfuric acid concentrations. In the last few years, coal-fired utilities around the country have been required to run at low load for extended periods of time. This reduced operating temperature, when combined with SO3, wreaks havoc on mercury control. If SO3 concentrations are high enough and gas temperatures low enough, the SO3 and sulfuric acid will combine with ammonia to form ammonium bisulfate, ABS. This ABS condenses inside air preheaters, causing corrosion and pluggage. But the relationship to mercury emissions is also important, as ABS sticks to the surfaces of catalysts, reducing its overall surface area and efficiency. Clearly, this hinders the ability of the SCR to oxidize mercury. The ABS formation temperature is a function of several variables, including ammonia and SO3 concentration. If SO3 concentrations can be reduced, it is possible to run a coal-fired unit at a lower minimum operating temperature without creating problems for the SCR and air preheater. It is also well known that SO3 competes with mercury for active sites on LOI, activated carbon, and other sorbents used for mercury control. Minimizing SO3 concentration leads to better capture efficiency of the sorbents being used for mercury control, allowing for lower injection rates and less sorbent usage. In fact, some work has even been done recently to eliminate injection of carbon altogether and switch to a strategy of reduced SO3 in conjunction with increasing LOI to control mercury levels. SO3 is a really important variable to evaluate whenever you see higher than expected mercury concentration. Dropping sulfuric acid might hold the key to optimizing your SCR and mercury control strategy. And this is such an interesting phenomenon. I always make new friends when I talk about dropping acid with my customers. Really interesting friends, in fact. So, one of the ways to reduce SO3 concentration is to use dry sorbent injection, or DSI. SO3 sorbent traps are a great tool to evaluate the effectiveness of this approach. A typical engineering study using SO3 sorbent traps involves sampling at the inlet and the outlet of an SCR while injecting DSI upstream of the SCR, then varying the DSI injection rate to determine how much SO3 is removed at each rate. This sort of test allows plant operators to know how much DSI is required to reduce ABS formation temperature to an acceptable level, thereby enabling the plant to run at a reduced load. And SO3 sorbent traps are extremely temperature sensitive, as the traps are designed to capture total SO3 gas, H2SO4 gas, and H2SO4 liquid. These forms all exist in equilibrium, and their concentrations are a function of total concentration, temperature, and percentage of moisture. The sorbent primarily reacts with H2SO4 gas, so sampling conditions must be such that this form dominates. This is primarily done by controlling sampling temperature very precisely using our cooling probe and the fine temperature controller with inline thermocouple that I described earlier. Sulfuric acid vapor is highly reactive and sensitive to changes in matrix, including extraction and dilution. This is why controlled condensate results are often so variable. The best sampling approach is to capture in situ, and this is the reason we've focused our development efforts on SO3 sorbent traps. Also, with SO3 traps, you are not just following a recipe and hoping for a good outcome. Instead, you're validating each and every run. In order to call your data valid, you must pass the QA/QC requirements that are similar to reference methods such as Method 30B. You must sample in duplicate, you must pass paired agreement and spike recovery, you must pass breakthrough on every trap. You have to validate every single run. So we discussed the SCR and its ability or hindered ability to oxidize mercury. Now let's make our way to the FGD. A measurement of oxidized mercury versus elemental mercury at the inlet of the FGD should give you a good indication of how efficiently you are able to oxidize mercury as a co-benefit of your plant's pollution control equipment upstream of the FGD. Then, since oxidized mercury is soluble in water, it can be removed from the flue gas by the presence of a wet FGD. Elemental mercury is not as soluble and mostly passes through the FGD. So a measurement of elemental mercury at the inlet of the FGD should give you a good indication of what your mercury emissions should be coming out of the stack. But for some wet FGDs, when oxidized mercury enters the scrubber, it is chemically reduced to elemental mercury and released out of solution back into the gas. This phenomenon has been coined mercury re-emission and is defined as an increase in elemental mercury across the wet FGD or scrubber. Basically, stack mercury is greater than the inlet of FGD elemental mercury, and that's what we would coin as mercury re-emissions. There are many mechanisms in play here. Sometimes it's really challenging to make sense of it all. Swings in liquor pH can lead to mercury re-emissions events and total stack mercury excursions. Some have reported low pH, less than 4.5, produce increased mercury re-emission, while others report higher pH promotes mercury re-emission. This seems inconsistent, but it is really the unique combination of these variables and their impact on ORP and transition metals that yield unit-specific mercury re-emission. The natural oxidation rate is influenced by a combination of the sulfur loading of the unit and the liquid to gas ratio, along with other factors. These other factors include slurry depth, location of air injection, and bubble fineness. Increasing the amount of forced air has been observed to suppress mercury re-emissions, yet other studies have concluded that increased airflow results in higher mercury re-emission. Again, testing on a specific unit is necessary, along with characterization of the unit, including scrubber liquor ORP and sulfite and mercury concentrations. The oxidation reduction potential of the scrubber liquor is a relative measure of the propensity of the medium to be chemically oxidizing, attracting electrons, or reducing, losing electrons, and is yet another confounding variable. It would follow that a positive ORP value would suppress the reduction of mercury and thereby suppress mercury re-emissions. There's even ORP modification additives that have been suggested to promote higher ORP. On the contrary, other studies suggest lower ORP is optimum. The determination of an appropriate operational range for ORP is dependent on parameters specific to a unit. One thing is consistent. Testing must be conducted specifically for each individual unit and its unique FGD chemistry. For plants with multiple units, this comes up all the time. Even identical units are not the same and are almost never the same. The reactions are still typically very different. Accurate measurements are critical and ideally should be done simultaneously at the wet FGD inlet and the stack. So how do we do those measurements? The best way to accurately measure mercury speciation is in a twofold approach. Mercury speciation sorbent traps are an excellent tool. You just have to be wary of their temper, which we discussed previously. But the addition of a temporarily installed real-time mercury process monitor that can speciate will allow for you to see re-emissions in real time and as you make process changes or vary injection rates for various FGD additives or oxidation chemicals. There's one other thing we like to look at when it comes to mercury and the wet FGD, and that is the actual mass balance of metals in the FGD slurry. The thought process is that it is important to make sure that dissolved mercury is kept to a minimum to prevent re-emissions in the stack. It is then helpful to precipitate the dissolved mercury. And for some sources, it is helpful to precipitate dissolved selenium to help meet effluent limitation guidelines. It is even common to inject additives into the slurry to help precipitate these compounds. With this in mind, we developed a method for determining the mass of liquid and solid components in the FGD slurry. We take the slurry through a 0.45 micron filter to separate the filtride from the filtrate, and then measure how much mercury or selenium are in each component. This is a data set showing the material balance and mercury concentrations for a set of 4 samples. As you can see, most of the mercury is found in the filtride, or solid component. The percent of solid component in the slurry was measured at around 18% by mass. The goal is to reduce the amount of dissolved mercury in the filtrate, as this is the component where mercury can be reduced into its elemental form and re-emitted. We can do this by moving the mercury into the solid filtride from the filtrate through precipitation. In this data set, upon increasing the injection of an additive, you can see that the amount of dissolved mercury is reduced from around 1 nanogram to 0.3 nanograms, which reduces the amount of mercury that could be released during a re-emissions event. This result confirms the performance of the additive, and though it looks minor, this change is actually pretty substantial. One more interesting pattern I want to discuss is high mercury upon startup after a planned or unplanned outage. This phenomenon is difficult to detect unless you separately sample sorbent traps during startup or have a mercury process monitor, which allows for you to see mercury concentration in real time. We're often alerted to this phenomenon because customers will think that something is wrong with their mercury process monitor. We come on site to verify the SEM and see that it matches the traps. So what is going on? As ducts heat up slowly, residual mercury that has lined and accumulated along the surfaces begins to vaporize. This mercury eventually mixes with flue gas and is removed or emitted. SCRs also run into many complications when operating at lower temperatures and when load is cycling or less than anticipated in the design of the SCR. As for the FGDs, even during normal operations, they are not entirely normal. In a steady state, startup of a unit after an outage is a whole other unique condition and is impacted by things like the initial scrubber liquor charge and unit startup procedures. Aside from startup, load swings also create unique conditions around the wet FGD. And even changes in sulfur dioxide content at the inlet resulting from fuel changes impacts wet FGD scrubber chemistry. Scrubber chemistry is complicated. But luckily, there are many tools at your disposal where you can evaluate where these high mercury events are taking place and why. And I just want to tell you guys, thank you so much for listening. If you have any questions, please do not hesitate. You can always reach me on my cell phone. That's the number that's on the screen right now. Or you can reach me by my easy email, which is alex@ohiolumex.com. Thanks again for coming, and I really enjoyed our time. Let me know if you have any questions.